Alrighty, so today we're going to begin our introduction into probability. Okay, a lot of us have differing backgrounds when it comes to probability, so we're going to kind of just move our way through reviewing what's review. If something seems a little bit new, that's great. Just, jot it down as you need. Excuse me. So, the first thing that we want to review are independent events versus dependent events. Okay? Independent events do not affect each other. They are separate. The outcome of one does not affect the outcome of the other. Dependent events, on the other hand, those do affect each other. All right, so an example of an independent event would be if I spun a spinner 3 times in a row. Well, the outcome of the first 2 spins does not affect the outcome of the third spin. Those would be independent. Now, dependent would be, say you had a bag of marbles. You drew a marble, and you left it out on the table before drawing the next one. Okay? Then whatever you drew the first time does change the probability for what you're going to draw the second time. So independent versus dependent events. All right. So our first example we're going to talk about is tossing 3 coins, or flipping 3 coins. Now, it really doesn't matter that these are 3 separate coins, or even if I just said flipping a coin 3 times in a row. Those would each still be independent events. Everyone okay with that? All right. So first what we're going to do is we're going to use a tree diagram to list out all the possible outcomes of flipping those 3 coins. Excuse me. So let's say we toss the penny first. What are the 2 possible outcomes when I toss the penny? Heads and tails. Goodness, all right. All right, so that's the penny. Everyone okay with that? 2 outcomes, what's the probability of each? 50% or 1/2. All right, now I'm going to toss a nickel. Now, when I toss the nickel, I have 2 options, right? Heads or tails. So after tossing the penny and getting heads, when I toss the nickel, I can either get heads or tails. After tossing the penny and getting tails, when I toss the nickel again, I can get either heads or tails. How many total outcomes are there now? 4. Heads, 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 tails, tails, heads, tails, tails. 4 total outcomes now. Everyone okay with that? Okay. Now I'm going to toss the dime. For the dime, there's 2 possible outcomes, heads or tails. But that's out of each of these original outcomes. So I could toss and get heads, tails, heads, tails, heads, tails, and heads, tails. So now, how many total outcomes are there? Yeah, there are 8 total outcomes. What is the theoretical probability of getting any one of these 8 paths? Yeah, 1/8. Okay. Any path I draw, that's 1 path out of 8. So the theoretical probability for any combination is 1/8. Okay. What if I flipped an additional coin? How many total outcomes would there be? 16. It would double, because out of each of these, I'd have 2 more. Okay. It's 2 raised to the power of how many coins are flipping. So when I flip 1 coin, I have 2 outcomes. When I flip 2 coins, I have 4 outcomes. 3, 2 cubed is 8. 2 to the 4th would be 16, to the 5th, 32, and so on. Okay? Now this tree diagram can help us out, okay? We can also do these things using properties of probability. So you kind of just got to decide which one makes more sense to you. All right? So let's find the probability of flipping 3 heads. So that P parentheses basically means the probability of 3 heads. So looking at our tree diagram, how many paths has all 3 being heads? Just one of those paths. So using the tree diagram, that's 1 path out of the 8 paths, which gives me 1/8 probability. Yeah, we're going to use fractions. Okay? We're going to use fractions, yes. All right, now let's talk about that numerically. To get 3 heads, okay, that means I want a head on my first flip, head on my second, head on my third. Now, do I want one of these to happen or the other ones? No, I need all of these to happen, right? So I need heads on the first one, and heads on the second one, and heads on the third one. Now, in probability, and implies multiply. So what's the probability of flipping your coin and getting a head? 50%. Okay, 1/2. And then getting a head on the next flip is again 1/2. And then again it's 1/2. So 1/2 times 1/2 times 1/2. I multiply across the top. That's 1. And I multiply across the bottom. And that's 8. Questions on that? All right. Let's talk about the probability of getting 2 heads and 1 tails. Now, it does not specify 2 heads, then a tails, or heads, tails, heads. So it means it can be any combination of 2 heads and 1 tails. So trace your paths on your tree diagram and see how many paths would give you, don't call it out, but how many paths would give you 2 heads and 1 tails. How many paths will give you that? 3. 2 heads and 1 tails. Could be this one, heads, heads, tails. It could be heads, tails, heads. Or it could be what? Tails, heads, heads. So that's 3 paths out of 8 paths. All right, let's think about it using properties of probability. What are the options that we just listed out? Well, we could have heads, heads, tails. We could have heads, tails, heads. We could have tails, heads, heads. Now, do I want these all 3 to happen? I want 1. So I want this, or this, or this. And in probability, or means addition. So each of these paths has a 1/8 probability, right? Half times 1/2 times 1/2. So this is 1/8 plus 1/8 plus 1/8, which gives me my 3/8. Questions about that?
So to get 1/8, did you do heads and heads and tails and then each head?
Mm-hmm. All right. Oops, sorry. Now I want the
Every time.
now I want the probability of getting at least 1 head. Probability of getting at least 1 head. Now let's think about what that means. At least 1. At least 1 head means what?
There has to be one.
Greater than or equal to.
Okay, so 1 head, 2 heads, or 3 heads, right? Okay, so look at your tree diagram. How many paths have at least 1 head? Yeah, 7. There's 1, 2, 3, 4. Everything up here, right? Because we have this head. And then 5, 6, 7. Y'all see that? So that would be 7 out of 8. Now I heard some of y'all say all but 1, or anything except all tails, which is another great way to think about these at least problems. Another way to think of them is to think of 1 minus the probability of the opposite. Well, what's the exact opposite of at least 1 head? All tails. I'm going to go ahead and say no heads, just so we stay consistent. Okay? And no heads only happens when you have tails, 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 right? Which is 1/8. So this is 1 minus 1/8, which gives us the 7/8. This would be good if you had more coins or more outcomes so that you didn't have to count them all up. You could just do the 1 minus. All right, questions on our coin scenarios? All right. Another big thing in probability is a deck of cards. Now, for a lot of you, this is common knowledge. You know this, okay? Some of you who aren't as familiar with cards might want to jot this down. This is knowledge that you're expected to have in order to execute a problem, okay? A standard deck of cards has 52 cards. They are half and half, black and red. Within the 26 black cards, you have 2 suits. 13 cards are clubs and 13 cards are spades. Within the red cards, you've got 2 suits. 13 are hearts and 13 diamonds. So your 4 suits are clubs, spades, hearts, and diamonds. Each suit has 13 cards. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Queen, and King. So again, if this is not something you are familiar with and really comfortable with, jot it down so that you can memorize it. Correct. Standard deck is only 52 cards. No jokers or anything like that. Anyone need more time getting this done? All right, let's keep going. So, if I draw 1 card at random, I want to know the probability that that card will be a 7. All right, well, let's think. How many 7s are in the deck? 4. Out of 52. Okay, and what is 4 out of 52 reduced to? 113. All right, that's pretty straightforward. Let's think about another one. What's the probability, if I draw 1 card at random, that that card would be 7 or red? Now, the tricky thing here is that some of the 7s are red. So I've got to be careful not to double count any cards. Okay, so let's think about first. The probability of drawing a 7 is 4 out of 52. Or means we do what? Add. Probability of drawing a red card is 26 out of 52. But what you have to do then is subtract out any cards that you counted twice. So how many cards were present in each of these numbers? 2. The 2 red 7s. So then you have to subtract out those 2 cards because you can't count them twice. So 4 plus 26 is 30 minus 2 is 28 out of 52, which reduces to what? Okay. Yes, ma'am.
If you can you just do like count all the red and then count what 7 is left?
Yeah. No, if you can kind of do this in your head, say, okay, there's 4 7s and then there's 24 more red cards, and that gets you straight to the 28, that's fine. At some point, though, you just have to take into account that you can't double count. All right. Probability of drawing a queen or a king. So what's the probability of drawing a queen? 4 out of 52. 4 means we add. What's the probability of drawing a king? And what do you get? Yep, 1/13 plus 1/13 gives me 2/13. Questions on that? All right. This time I'm going to draw 2 cards with replacement. Meaning I'll draw the first card, put it back, draw the next card. So with replacement means that I'm going to have independent events. All right.
So it's
Look.
basically the same. Sort of.
Okay, so let's look at this. We're going to draw 2 cards with replacement. So I want to know the probability of drawing a queen and then the probability of drawing a king. So first, what's the probability of drawing a queen?
4.
All right. And then we want to draw a king. So again, it's going to be 4 out of 52, and we're going to multiply because we want the first one to happen and the second one to happen. All right, well, this is 1/13 times 1/13, which gives us 1 out of 169.
This is the probability of drawing a king and queen.
Probability of drawing a queen, and then putting cards back, shuffling it up, and drawing another king. Okay. Now let's look at 8. I want to know the probability of drawing a queen and then another queen with replacement. So what's the probability of drawing the queen the first time? 4 out of 52 or 1/13. And then I want to draw another queen. Yeah, again, it's still 1/13 because I put the cards back. So 7 and 8 have the same probability because we're talking about with replacement. Okay, let's look at number 9. The probability of drawing the ace of spades and then drawing the ace of spades again. So what's the probability of drawing the ace of spades the first time?
1 out of 50.
Good. And then it's with replacement, so we're going to put it back. And again, we have 1 out of 52. So 1 times 1 is 1. And what is 52 times 52?
2,704.
Good. Okay. Now those 3 examples were with replacement. Those were independent events. We're going to repeat each of these situations now without replacement. Okay? Meaning once we draw the card, it stays out. So these now become dependent events because whatever I get the first time will affect the outcome of the second. All right, so I'm going to repeat the first one, the probability of drawing a queen and then a king without replacement. So the probability of drawing the queen on the first draw would be 1 out of 13. And then I want to draw a king. Well, have I taken away any kings? No, there's still 4 kings. There's only 51 total cards left. So that gives me 4 over 663, which you would double check and see if it reduces using your math frac. Thank you. Does it reduce?
No.
No, so we would leave this as our fraction. All right. Now, again, without replacement, I want to know the probability of drawing a queen and then another queen. So the probability of drawing the first queen would just be 1/13. When I go to draw the next queen, though, how many are left? Now, how many queens are left?
3.
3. So instead of 4, it would be 3 over 51. Because that card that I drew the first time was supposed to have been a queen. So this gives me what?
4 over 2 and 1. 4 over 2 and 1.
Good. It would be 3 over 663, which reduces to 1 over 221. Right? Then I would want to do the probability of drawing the ace of spades and then the ace of spades. It would be impossible. Let's see why. How many ace of spades are there? Just 1. So the probability of drawing the first one is 1 out of 52. After you draw it, though, there's none left. So it'd be 0 out of 51, which is just 0. What does a probability of 0 imply? It's impossible. Zero would be your answer because it asks you what's the probability.
So couldn't you just say no probability? Or what is probability?
It's a probability of 0. Okay. All right, so here are some things that we've touched on today that I want you to remember. Okay. I want you to remember that we've talked about independent events versus dependent events. Independent means the outcomes do not affect each other. Dependent means the outcomes do affect each other. We've reviewed that with probability, and means multiply, or means add.
It's a comma, does that mean? Like if it says P parentheses thing, comma thing, that means and?
Because you're drawing 2 of them, and you want the first thing and then the second. All right. Getting a probability of 1 means that that's every possibility. Okay, so that means that that will always happen. For example, if I asked you what's the probability if you draw 1 card of getting a red or a black card? Well, the probability of getting a red would be 1/2, or black is 1/2, and that gives you 1. Okay, because every card is either red or black. Okay? Like we just saw, a probability of 0 means that that event can never happen. It is not possible. Okay? All right. Everything we did today was theoretical probability. Everything we did was what was supposed to happen. In a perfect world, perfect conditions, mathematically what's supposed to happen. Now, the counterpart of theoretical probability is experimental probability. Experimental probability is what actually happens based on trials. You'll often use proportions to solve your experimental probability or to make predictions based on your experimental probability. So let me give you a quick example. You can just pay attention if you want. Let's say I have a spinner. Okay, and in 100 trials, okay, I got 1 37 times, I got 2 20 times, I got 3 30 times, and I got 4 13 times. Right? Based on theoretical probability, how many should I have gotten for each of these in 100 trials? Yeah, you should have gotten 25 out of 100, or 1/4, right? But my experimental probability isn't necessarily going to always match my theoretical probability, okay, because it's based on real trials. Now, you can also be asked, based on your trials or your data or your experimental probability, how many times could you expect to roll a 3 in 500 trials? How could we set that up?
30 times
30 over 100 was equal to
x over 5.
x over 500. Okay, we can cross multiply, solve our proportion. You might also be asked, which experimental probability has the greatest difference from the theoretical probability? Okay, 1 is off by how many? 12. And how many, is anything else off that same amount?
4.
Yeah. So 1 and 4 have the greatest difference from their theoretical probability. So those are the types of questions you'll be asked with experimental and theoretical. Stuff you've seen before, a lot of proportion stuff. Okay? When you work on your homework over these next few days, your goal is accuracy. Okay? Being say 1 out of 52 off is a big difference in probability because you've missed a whole case, okay, or you've missed some intricate detail. So your goal over these next few days, gearing up for that accuracy homework check, is the accuracy, okay? When you get your homework, be sure to read your instructions, okay? The front page is kind of broken off into sections, and some of the sections say repeat with replacement or repeat without replacement, things like that. So some of them are going to ask you to do them twice. So make sure you read your instructions throughout the homework, okay? All right.